Hey yo, what is up? It's your boy, back at it again with another video. And today I think I wanted to go a bit more in depth with orbitals and what orbitals actually were in an atom, just kind of to add on to my last video, which by the way, had no sound. Yeah, the sound cut off, I can't really control that, but it is what it is. So, orbitals, well, first of all, last video we talked about how in quantum mechanics we can never really know the exact location of an electron. Electrons move in wave functions, and it makes it really hard for us to interpret where that electron actually is. The electron actually has no fixed position in the atom, but because we can't know where exactly the electron is, we can estimate or approximate where these electrons are most likely found. The area where electrons are most likely found are called orbitals. And let me write that down. It's a region where electrons are most likely found. And so orbitals are found in something called sublevels. Sublevels are collection of orbitals found at specific quantum energy levels. And these specific quantum energy levels are what we refer to as shells. For example, sodium, or let's do something easier. Lithium looks like this, right? Lithium has two shells, okay? This is n equals 2, and this is n equals 1. So we say the quantum energy level is denoted by n. Sublevels, on the other hand, there are 4 types of sublevels. There is the S sublevel, the P sublevel, the D sublevel, and the F sublevel. The IB only really requires you to be able to draw the S and P sublevels, so I will do that for you. So if I drew a 3D Cartesian plane, where this is, where this is the Z, this is Z, this is Y, and this is X. So that's our 3D Cartesian plane, okay? If I just copy that. This is what an S sublevel looks like. It's a sphere. And the S sublevel only has one orbital, okay? And that orbital, it can be denoted by a box, and this box is an orbital. The P sublevel has 3 arrangements. The P sublevel has three arrangements, and so for this I'll draw 3 Cartesian planes to show you that. So the P kind of looks like a figure 8. So there's a figure 8. There's a figure 8 that's drawn along the x-axis. This orbital is called the px orbital. Then there's one that's drawn along the y-axis. This is called the py orbital. And there's one that's drawn along the z-axis. This is called the pz orbital. Every configuration has one orbital, which means in total P has 3 orbitals. In total, S has 1 orbital. D, you don't need to draw it, but D has 5 configurations. This means the D sublevel has 5 orbitals. The F has 7 configurations, so it has 7 orbitals. Every orbital can hold up to 2 electrons. This means S has a max of 2 electrons, P sublevel has a max of holding 6 electrons, D has a max of holding 10 electrons, and F has a maximum of holding 14 electrons. This is the basis of orbitals and sublevels. And if you remember last video, I kind of touched on Gauss' principle, stating that the orbitals of lowest energy are filled first. And characteristically, 4s is filled before 3d because 4s has less energy than 3d. 3d just has a lot of orbitals, so typically it has a slightly higher energy level than 4s. So let me do a bit of example. Just a couple examples. Say I wanted to give the box diagram of let's say magnesium. What we do first is we'd locate where it is. So every row on the periodic table denotes an energy level. So manganese is found in the 3rd energy level in the S block with 2 valence electrons. So the address of the final electron for manganese is 3, which denotes the energy level, and it's also found in the S block, which denotes the location, the sublevel of its final electron. And because it's in this second column, we know that it's filled with 2, so it's 3s2. That's the address of the final electron, which means we'll have to draw box diagrams for every orbital up until 3s. So let's do that. This is 1s, this is 2s, this is, let's draw that a bit bigger. This is 2p. And then this is 3s, okay? So according to Hund's rule, orbitals of equal energy are each occupied by 1 electron before any pairing occurs. So we do this. 1, 2, 3, 4, 5. Notice how I'm going to fill them. 6, 7, 8. I fill each orbital up first before I go back. 9, 10. And so this is how it would look like. In words, we'd say this is 1s2, 2s2, 2p6, and 3s2. But as you can notice, this in here is actually the electron configuration. This right here is actually the electron configuration of neon. And so neon's right here. The reason it's the electron configuration of neon is because all noble gases actually have a completely filled outer orbital, which means up until their final orbital, if it's filled up, we can call that a noble gas. And essentially, in shorthand notation, we find the closest noble gas to the element we're trying to configure, and we write it down along with the excess orbitals that are filled for the next one. So in this case, manganese can be written in shorthand notation as the electron configuration of neon plus 3s2. So this is what I call shorthand notation. The IB actually requires you to be able to do this and this and this. So 1, 2, 3. Okay, let's do another example. Say I asked you to find the electron configuration of manganese. So let's do box diagram for manganese. Pretty much, we do the same thing. We find the address of its last electron, which is found in the D block. It's found in n equals 4, but hold up. When we're working in the D block, we actually don't look at the column. We look at the, we don't look at the row, because right here the row is 4. We actually look at the row before it. So essentially, this wouldn't be 4D, it would be 3D. The rule is, in the D block, we think n minus 1. So it would be 3D. And how many electrons do we have? Well, if we start from scandium, this is 1, 2, 3, 4, 5. So 3D5. Therefore, we have to fill everything up to and including 3D. So let's do that. This is 1s, this is 2s, this is 2p, this is 3s, this is 3s, oh, sorry, 3p, not 3s, what am I saying? 3p. Remember, 4s before 3D. So remember Aufbau's principle, we fill them up one at a time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. In words, or in simply configuration terms, you'd write that as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. In shorthand notation, we'd find the nearest noble gas. In this case, the nearest noble gas is argon, so we'd write argon. And argon goes all the way up to 3p6. So argon is everything up till here, plus 4s2, 3d5. So I hope that video kind of cleared things up, and if it didn't, feel free to comment. In my next video, I'll talk a bit more about ions and first ionization energies, as well as first electron affinities and different trends on the periodic table.